Yeah, welcome. The topic we'll be discussing in this lecture is planning graphs. In the last lecture, we have discussed different types of heuristics, but in spite of using all those heuristics, the problem, most of the real world problem, even applying the heuristics also, the problem size will be pretty big, and hence solving that is not that easy. Okay, so in that context, we'll be discussing the next technique, which is called as planning graphs. Actually, planning graphs helps us to identify good heuristics. Using planning graphs, we can easily uh, identify some good heuristics. So normally in the state space search graph, in the state space graph, whatever the state space search algorithms we have discussed so far, there the state space is represented as a graph. In those graphs, nodes are nothing but states, and edges represent a path from one state to another state. Nodes represent states, and edges represents path from one state to another state. But in planning graphs, in planning graphs, so the topic we are going to discuss is planning graph. In planning graph, the nodes are actions and atomic facts. The nodes can be either action or an atomic fact. Nodes are not states. Nodes can be either an action or an atomic fact. And what is an edge? There are two types of edges. So nodes can be either action or an atomic fact, and basically there are two types of edges available. One is there can be an edge from an action to an atomic fact. This is one case. Okay, or there can be an edge from an atomic fact to an action. So these are the two types of this fact, atomic fact to an action. So these are the two types of edges the planning graph supports. Okay, so if the edge is from an atomic fact to the action for which it is a condition, it means that if an edge goes from atomic fact to an action, it means that for this action, this atomic fact is a precondition. If this precondition is satisfied, this action can be taken. That's the meaning. Similarly, if an edge goes from an action to an atomic fact, so that is an effect. When you perform this action, this is the result you are getting. So the result can be either true or false. So these are the two types of edges the planning graph supports. And the planning graphs are mainly they are used as a source of heuristic. Okay, so they are basically used to identify the heuristic function. So basically it returns an estimate of how many steps it is taken to reach the goal. So using the planning graph, we can identify. It is a heuristic value. It's not accurate value. So yeah, so it's a heuristic cost of how many steps it will take to reach the goal state. Right? Okay. So planning graph is an approximation of complete tree of all possible actions and their results. So it is an approximation of the complete tree of all possible actions and results. It is not a complete tree. First of all, it is not a complete tree. It is an approximation of the complete tree. So it is something like a reduced version of the complete tree. Right? And the planning graph is organized into levels, and the levels contains alternatively Si and Ai. So the first level starts with S naught. The first level starts with S naught, which represents the initial state, and this initial state may consist of nodes representing the fluent that holds in S naught level. Fluent means some atomic fact. Fluent means some atomic fact. So basically it represents the atomic facts that were true. Basically it represents the atomic fact that were true at the initial state. And A naught represents the actions that are applicable at S naught. So S naught and A naught is one level. Okay, this is one level. After S naught and A naught, you will have S1 and A1. This is another level. Then you will have S2, A2, so on and so forth. It goes on. So based on some condition, it will stop. Okay. So initially it is S naught. So S naught represents all the fluent. So fluent means, so basically S naught represents all the fluent which are true in the initial state. Okay. It represents all the fluents that are true in the initial state. So fluent, so here fluent in the sense it represents atomic facts. So basically it represents the atomic facts that are true in the initial state. Then for each of these atomic facts, what action you can perform, that is A naught. When you perform an action, some result will happen, that is S1. So this entire thing constitute one level, this constitute another level, so on and so forth. Right. So there will be alternate Si and Ai. Si contains fluent which can hold at time I. So any Si if you take, it represents fluent which are true at time I. And Ai contains actions which could have their preconditions satisfied at I. So this action can be taken if some preconditions at S1 is satisfied. If this precondition is satisfied, then this action can be taken. So that's what each Ai represents. So fine, let us try to understand planning graph with an example. So let us take this example. This is the initial state which says that have cake. Okay, there is cake is there. That's the meaning. Okay, have of cake. Basically, it means that the cake is available. And this is the goal state. The goal state says that have cake and eaten cake. The goal state says that there should be a cake and also and cake should be eaten. So there are two cases. So it means so you can treat as two different cakes. So it means there is a cake one that you have currently. There is another cake two that is already eaten. So something like that. Okay. So these are the actions we have. Eat of cake. So if you want to perform this action eat cake, then what is the precondition? Precondition is you should have cake. Have cake. Okay. So if have cake is true, then you can apply this action eat cake. If you apply this action eat cake, then what will happen? There is no more have cake. So not have cake and eaten of cake. These two things are happening. The old cake disappears and also eaten of cake becomes true. Next is bake cake. Bake cake is used to create a cake. Now what is the precondition for this? Not have of cake. Only if you don't have the cake, you can bake a new cake. Okay? And what is the effect? Effect is you will have a cake. Right? So this is the problem. This is a problem definition. For this, how can we draw the planning graph? That's what we are going to discuss. So this is the initial planning graph. It's an incomplete planning graph. So later we will discuss the complete planning graph. But let us try to understand this. So you can see here what is the initial state. As per this, the initial state is have cake. Okay. So in S naught we will have only have cake. In S naught we have only have cake. So this is a fluent which it is given. But have cake also means what? Have cake also means that not eaten of cake. So this is also true. Actually both are same only, right? Have cake means not eaten of cake. Okay. Fine. Now what action, if you have cake, then what you can do? So this action we are doing. If you have cake, you can just eat the cake. If you eat the cake, then what is the result? Not have cake. You don't have cake and eaten of cake. Right? But this is an idea to understand how the planning graph works. But this is not a complete solution. Okay. So here we have just what we are saying is the fluent is have, I mean the initial state is have cake. So that we got this. Okay. Now you have cake means it means what? Not eaten of cake. So we are adding this one more thing. This is just another way of representing this. Okay. And now we have an action eat cake. So eat cake's precondition is have cake. As the precondition is satisfied, we can apply this action eat cake. Once you apply this action eat cake, the result will be what? Eaten of cake and not have of cake. Right? Okay. So we have something called as persistence action. In addition to the normal action in the planning graph, we have something called as persistent action that we will be discussing soon. And also we have something called as mutex or mutual links. There is something called as mutex or mutual links that also we will be discussing. Okay. So here is so this is also an incomplete example. Here is another incomplete example for planning graph problem. So but here we are introducing a new action which is called as no operation. This action also you can include. So this action is called as no operation. So initially, what is the condition? We have cake. Have cake means not eaten of cake. Okay. Now this is a new thing we have identified. No operation means no operation also you can represent as an action. So on have cake, if you apply no operation, what will be the result? The result will be have cake only. Okay. Similarly, on not eaten of cake, here if you apply on not eaten of cake, here if you apply no operation, what will be the result? The result will be not eaten of cake only. Okay. Have cake. Already you have cake. For this, if you apply this action eat cake, okay, then what does it mean? Then what will the effect? You already eaten the cake. So the effect is not have of cake. Not have so you don't have cake and eaten of cake. Okay. But still this is not a complete planning graph. One more thing, here you can see some red color arcs. So basically they represents independence. How much this what do you call? How much is each actions or each fluent or uh, how much they are? What is the relation? So basically this this red line represents like this link is called as mutex link or mutual links. Basically this link is called as mutex links or mutual link. So it represents like how much whether these two things can happen parallelly or not. That's what it represents. Okay, so that it is called as mutex links or mutual links. Okay, so for example, see if you have cake, you eat cake. Okay, or if you have cake, you don't perform any operation, you continue to have cake. You are not going to eat it. Now these two operations are now these two tasks are what you call they are not they cannot happen simultaneously. If one thing is happening, then the other cannot happen. So here this link is called as mutex link. So wherever the two things which cannot happen simultaneously, that is called as mutex links. Okay, so here somebody is having a cake means he can eat a cake, and if you don't eat the cake, then you will have cake. So now these two events are uh, they are not they are mutually they are mutually exclusive. Okay, similarly if you see this eat cake and no operation, here also the same thing, eat cake and for not eaten of cake we have this no operation. So here also if you see the eat cake and no operation, these two things cannot happen simultaneously. So if you are eating cake, if you are eating the cake, then hmm, then probably this will not see. Only if you have cake you can eat cake. If you don't have cake, then you cannot eat. You have to go with no operation only, right? When you go with no operation, you will have not eaten of cake, right? So again here also if you see these are mutex links, that is they don't they cannot occur at the same time. So have cake and not have cake, these two incidents cannot occur at the same time. Any one can occur. Similarly, not have cake and not eaten of cake. This also cannot happen simultaneously. Not have means you don't have a cake. Not eaten means you have not eaten. But it is saying that you have a, so basically it means that you have a cake. Okay. So not have cake and not eaten of cake, they both actually contradict each other. Similarly, eaten of cake and not eaten of cake, these also contradict each other. So wherever they contract, that is, so wherever contract in the sense wherever these lines, this arc were specified, so basically it represents that those actions are mm, mutually exclusive. Okay. Right. Now there are three types of mutex. So this is there are three types of mutex. This mutual exclusion thing, it can be of three types. The first one is called as inconsistent effects. So when there is inconsistent effect, it will create uh, when there is inconsistent effect, basically it will create a mutex relationship. Okay, that is one action negates the effect of the another. So that will lead to inconsistent effect. For example, eat cake and persistence of have cake have inconsistent effects. Eat cake will lead to what? Eat cake. Eat cake means when you apply the action eat cake, then you will get not have cake and eaten of cake. Okay. So so when you say eat cake, so basically after eating there will be not uh, so after eating the cake, what is the two options we have? After eating the cake, we have eaten of cake and not have of cake. Okay. So so after eating the cake, we have after eat cake, we have eaten of cake and not have of cake. If you take this example, it is eaten of cake and not have of cake. Okay. And so so the point here is inconsistent effect. One action negates an effect of another. So so eat of cake, this is the effect. Eaten of cake and not have of cake. Now now let us consider this rule also. This fluent also have of cake. But we want to apply the persistence rule. But we want to apply the persistence rule. When you apply persistence rule, what you get is have of, that is basically we are applying no operation. So when you apply no operation, have of cake will be continued as have of cake only. Okay, it will be continued as have of cake only. Now these two things are mutually exclusive, right? First here we got not have of cake, but here we are getting have of cake. So they are mutually exclusive. So they should be represented with this type of arrow. That's what it represents. So this mutual exclusion basically is of three types. This is the first one, inconsistent effects. Right? The second method is interference. Second is interference. It is one of the effects of one action is the negation of the precondition of the other. One of the effects of one action is the negation of the precondition of the other. Okay. When you perform some action, that is actually negating the precondition of the other. Such, what do you call? such things also comes under mutex, right? Because if one person is doing, it is affecting the other person, and if the other person is doing, it is affecting this person. Okay, so that type of heuristic is called as interference. So here is an example for interference also, I think. For example, eat of cake interferes with persistence of have cake. Okay, so basically they are contradictive. So for example, if you take eat of k, it interferes with the persistence of have cake. So eat of cake is nothing but eaten of cake and not have of cake. Okay, but you have a function which is called as have of cake, and have of cake, I mean it's not a function, it's a literal. Or okay, and have of cake and eat of cake, they are actually mutually exclusive things. Right? So there is another reason for this mutex link. The third reason is competing needs. One of the preconditions of one action is mutually exclusive with the precondition of the other. So basically it means that one of the precondition of one action is mutually exclusive with the precondition of the other. Okay. One of the precondition of one action is mutually exclusive with the precondition of the other. That is, if this precondition is satisfied, then the other action cannot be satisfied. They are mutually exclusive. Here is an example. So eat cake. Here we have eat cake. The preconditions for eat cake is have cake. Okay. And for bake cake, it has a precondition not have cake. So this is basically an example of competing needs. Because for eat of k, the precondition is have of k, and for bake of k, the precondition is not have of k. So only one thing we can do. We cannot do both. They are mutually exclusive things. Right? Okay. So here is the complete planning graph. Right? So initially, if you see at S naught, there is only one info we have, which is have cake. But have cake also implicitly mean that not eaten of cake. Okay. Now with have cake, what you can do, you can apply no operation. When you apply no operation, the result will also have cake. Similarly, for not eaten of cake also you can apply no operation. The result is also not eaten of cake. But for have cake, you can apply another action which is called as eat cake. So when you eat cake, you don't know, you no more you have cake. So not have of cake and eaten of cake. Okay. Whereas other parameters are passing on as it is. Right? Because this is a no operation thing. So here the have cake, it's just passed on here. Similarly, this is also no operation. So this not eaten of cake is just passed on to eaten of cake. Okay. So here wherever there is a gray lines, there is this red line. So basically uh, they are mutually exclusive things, right? Fine. So now there is a question like, when should we stop this planning? So we should stop the planning if we encounter two rows were identical. We should stop when we encounter a situation where two rows were identical. Just a minute. So basically these red line represents, these are mutex operations. That is, they are mutually exclusive operations. If one is happening, the other cannot happen. Now this planning graph, when should we stop? We should stop when two levels are same. For example, this level, if you see this level and this level, they are not same. This level we have only have cake and not eaten of cake. But in this level we have cake, not have of cake, eaten of cake and not eaten of cake. So we should continue for one more round. So here if you see this S1 and S2, they both were same. So now we can stop the algorithm. Right? Because here we have cake, not have cake, eaten cake and not eaten cake. Here also we have the same thing, have cake, not have cake, eaten cake and not eaten of cake. Okay. So now you may ask like how we got this. So right, so this part is clear, right? So here have cake, no operation, we have cake. Not eaten of cake, no operation, not eaten of cake. Have cake, we can also do eat cake. So when you perform eat cake, you'll have not have cake and eaten of cake. Okay. Now again for each of these, now there are four, here we have four fluents. For each of these four fluents, you can apply no operation and some cases some action. For have cake, you can apply no operation. No operation, if you apply, the result is also have cake. For have cake, you can also apply bake of cake. So for have cake, not bake of cake, you can also apply eat cake. If you apply eat cake, then the result is not have cake and eaten of cake. Like that for everything you can do. For not have cake, no operation, the result is not have cake. And for not have cake, another thing we can do is bake cake. As we don't have cake, we can bake a cake. Bake cake, the result is have cake. For eaten of cake, we can apply no operation, then it is eaten of cake only. Nothing else we can do. For not eaten of cake, also you can apply no operation and not eaten of cake. Okay. So the point is here, if you see these things are same as this thing. Hence at this point we can stop the algorithm. And wherever, so everything you have to compare with every other thing and you have to check whether they are mutex or not. For example, have cake and not have cake cannot occur simultaneously. So this is a mutex link. Have cake and eaten of cake. Okay. So if you see have cake and eaten of cake, these two things also cannot apply simultaneously. Here also you have a mutex link actually. Then have cake and not eaten of cake, this can occur simultaneously. Have cake means it is not eaten of cake, right? Okay. So like that you have to check for everything. So if you see eat cake and not eaten of cake, it cannot happen simultaneously. Not have cake and not eaten of cake. Not have cake means you have cake. Okay. Not eaten of cake means the cake is not eaten. So not have cake means you don't have a cake. Okay. And not eaten of cake means you have not eaten of cake. You have not eaten the cake. But only if you eat the cake, then only you don't have the cake. So these two things also cannot occur simultaneously, right? So basically whichever the things which cannot occur simultaneously, that is represented using this red mark. So here also bake cake and eat cake, these two cannot happen simultaneously, because only if you don't have the cake you will bake the cake, right? So okay, so like that there are there are many operations which cannot happen simultaneously. Okay. So here if you see bake cake and this no operation cannot happen simultaneously, because if you don't have cake, either you can continue with no operation and you can continue with not have cake, or you have to bake the cake. So any one of them only can happen, both cannot happen, right? Similarly when you have cake, you can either continue with no operation and keep in have cake, or when you have cake you can eat it. So any one of these will happen. Similarly here also, eat cake and no operation. These two cannot happen simultaneously. So they are represented using mutex link. So eat cake happens when you have cake, and not eaten cake, this happens when you don't have a cake, right? So any one only will be true, right? Similarly for this also, eat and not eaten. So if it is eat cake, then this will be applied, otherwise this will be applied. Similarly for this end also. So whichever that cannot happen simultaneously, they are represented using that red lines. Fine. So this is how we create the planning graph. Now let us try to understand how, from a planning graph, how can we perform heuristic estimation. Okay. So actually the planning graph contains rich information. The primary information it contains is, if any goal literal fails to appear in the final level of the graph, then that problem is unsolvable. See, if you, I mean in the planning graph, say for example, you are looking for one particular goal, something x. If that x is not available in the final level, then it means that the problem is unsolvable. Okay. So your goal should be available in the final level, then only it is solvable. Otherwise by looking at the planning graph itself, you can say that it is unsolvable. That is one observation. And there is something called as level cost of GI. This level cost of GI is an estimate. We can estimate the cost of achieving a goal literal GI from the state S as the level at which GI first appears in the planning graph constructed from the initial state S. The level cost GI is an estimate. You can estimate the cost of achieving a goal literal GI. So we are looking for a goal GI from the state S as the level at which GI first appears in the planning graph starting from the initial state S. So the point is, you are looking for a goal GI, but we will start from the state S. Start from the state S and find where it is available and count. So that is called as level cost. Okay. So after S naught there will be A naught. First you check whether whether the goal is available in S naught or not. No, then go to A naught. Is it available? No, then go to S1. Is it available? Then go to A2. So on and so forth. Finally, at some place you will identify that is available. Then the cost is this, how many links you have paused. That is the cost. So that is called as level cost. This is one level. This is two level. This is three level. Right? Okay. So in the previous example, if you see, have cake has a level cost 0 and eaten cake has a level cost 1. So how we got this value? If you refer this planning graph here, have cake, it is coming at 0th level. So if your goal is to find have cake, then at 0th level itself you can find the goal. Okay. So the value of have cake, right? The level cost of have cake is 0. And if you consider eaten cake, consider eaten cake, its level cost is 1. Now see, the level means, previously I said this is one level and this is one level. It's not like that. This entire thing is one level. S naught A naught is one level, S1 A1 is next level, S2 A2 is next level, so on and so forth. Right? So here so we have to check two things: have cake and eaten of cake. So eaten of cake, here we don't have eaten of cake. Here we have eaten of cake. So eaten of cake is available at which level? It is available at level 1. It is available at level 1. Hence we got this value. The level cost of have cake is 0. The level cost of eaten of cake is 1. If you want to estimate the cost of a conjunction of goals, there are basically three approaches to do this. So conjunction means we are not going our goal does not contains one literal. Our goal contains multiple literals. It is something of this form: A and B and C. So A is one goal, B is one goal, C is another goal. All these goals should be satisfied. So how will you estimate the heuristic cost of a conjunction of goals? That's what we are going to discuss. So basically there are three ways to do this. The first method is called as max level heuristic. This max level heuristic, what it says in the sense, you find the level cost of individual goals. For goal A, what is the level cost? Identify. For goal B, what is the level cost? Identify. For goal C, what is the level cost? Identify. Out of this, whichever the level cost is maximum, that we will return as the heuristic cost. So that is called as max level heuristic. If the level cost of A is 2, B is 3, C is 6, then our heuristic cost will be 6. Okay. The second type of heuristic is called as level sum heuristic. The level sum heuristic basically returns the sum of the level cost of the goals. So it adds all the level cost and it returns that. Okay. So this max level heuristic, basically this will be admissible but not accurate. Accurate in the sense whatever it is saying, it may not be correct. Okay, but it is admissible. That is, it underestimates. It underestimates, but the heuristic function is not going to give any accurate answer. It is an estimate only. Hence we are saying it may not be accurate. If you see the level sum heuristic, here we add all the heuristics. So for example, there are three sub goals: A, B and C, right? Okay, say for A the level cost is as usual 2, and for B it is 3, and for C it is 6. In this case we add everything. In the first case, what we do in max level, we have identify the one with the maximum level cost. Okay, and that was considered as the heuristic cost. Whereas in level sum we add up all these things: 2 plus 3 5, 5 plus 6 11, and now we say that this is our heuristic cost. So this can be inadmissible. We are adding, hence this value is increasing, so sometimes it may be inadmissible. That is, it may not underestimate the goal state. Okay, but it is good in practical problems that are largely decomposable. For decomposable problem, for large decomposable practical problem, this type of heuristic was used in case of planning graphs, right? Okay, and the next type of heuristic is set level heuristic. With set level heuristic, we find the level at which all the literals in the conjunction goal appear in the planning graph. Okay, without any pair of them being mutually exclusive. So here what do we mean in the sense, the goal state contains multiple literals, right? So set level heuristic means it says that there should be some level where all these literals appear, A, B and C, okay, or whatever the literals. So that level, at which level all these three things has appeared, so that is called a set level. Okay. So fine, so that's it about today's discussion about planning graph. We'll stop here. Further we'll continue in the next class.